Okay, first of all, let me thank the organizers for giving me the opportunity to share this excitement of the LHC physics with you. And since this is the first of the only two experimental talks at this conference, I'll try to be gentle and won't give you much of the experimental details, but rather focus on the big picture and try to also emphasize some possible connections of what we are doing at the LHC with this big theory. So essentially, this is the short outline of my talk. I have probably more slides than I'll be able to show, but they would be in the posted version in case you're interested. And I'll talk about the highlights from what we call LHC Run 1. That was the first run which finished earlier this year. And talk about the path over the high luminosity LHC and the excitement physics program we plan for the next 20 years or so at this machine. So let me start by just thanking the machine and reminding you how successful the last 3 years of Run 1 were. In fact, what you could measure the performance of the accelerator is the units which we call luminosity, which is essentially number of collisions happening at the LHC. But more interesting units is how many Higgs bosons we, for instance, produce. And in 2011 run, we produced about 90K of Higgs bosons. That wasn't enough for us to claim the discovery, but with the full run, we now have over 500,000 Higgs boson produced, and essentially we needed roughly twice this number to claim the discovery in July. So this is really a fantastic performance of the machine. We have about 30 inverse femtobarn at 2 machine energies, 7 TeV and 8 TeV delivered. And the machine was actually increasing its performance with time. So you could see that it used to be available just, I don't have all the Korean fonts, looks like, in my talk. That's okay, I'll just skip to the next slide. And essentially in 2012, the machine was available for physics 30%, 36% of the time. So this is quite impressive. Thank you. So machine was available for physics 30% of time. All right, detectors also performed spectacularly over this run. This is how ATLAS and CMS experiment, the 2 major experiments at the LHC, looked like after the run. And you see they're approximately 99% functional after 3 years of operation. So there was no real aging, same for LHCb and ALICE experiment. So one important thing which we learned how to deal with in 2012 was the so-called pileup. The interactions at the LHC happen at a very, very high rate. And we never see just one single interaction between the quarks inside the protons. Instead, we see a mass like that, where we have to find the one interaction which was interesting. The one interaction, for instance, here produced the Z boson decaying to 2 muons. And sorting through this mass is not really easy. So we call this pileup, and we developed important tools to mitigate the effect of the pileup. This is just like cleaning the photo from the white noise you have, which you could do with good filters. And essentially with this pileup, average number of pileup interactions was 20 in 2012 run. And we learned how to sustain the efficiency of, say, muon reconstruction independent on the number of vertices, and also the resolution of missing transverse energy in the event. This is something we use to infer the presence of interacting weakly interacting neutral particles, such as neutrinos or dark matter particles, also stays almost constant as a function of pileup. So this mitigation really allowed us to use the machine to its full potential at very high luminosities. So let me show you just a few milestones from the LHC from 2008 to 2012. Well, the first beam was inserted in the machine on 10th of September of 2008. It wasn't quite well centered, but it was there. Unfortunately, a few days later, the machine broke down, and it took us about a year to recover from the melted dipole interconnect, which stopped us from operation for a whole year. The first paper from the LHC from ALICE collaborations appeared on 28th of November of 2009. A year later, in September of 2009, CMS published a paper on the so-called REACH, which is the correlations, long-range, same-side correlations, which before were seen only in lead-lead collisions, so heavy ion collisions, but we saw it in the high multiplicity events in proton-proton collisions, which was quite puzzling. And then the next milestone was the discovery of the first particle at the LHC, which wasn't the Higgs boson, but was one of the excitations of quarkonia Chi3p b, which was discovered by the ATLAS experiment. And then, of course, on July 4th of last year, almost a year ago, we celebrated the discovery of the Higgs boson, and the final milestone happened just a few months ago when LHCb showed the first evidence for B sub s decaying to mu mu at this machine. So the question, of course, what are the next surprises? The interesting thing about the LHC that allegorically it replaced three types of machine in one shot. It replaced the Tevatron in terms of Higgs searches for new physics, top physics, precision electric measurement. It replaced the B factories in terms of its ability of precision B physics, and it replaced the RIC in terms of the heavy ion physics. And the LHC experiments are very successful in all these three areas. And this work would not have been possible without a lot of theoretical and phenomenological breakthrough of the past decade, which have been encapsulated in the Monte Carlo, including, for instance, the string methods of calculating QCD diagrams from twistor space. I'll present a few highlights from these first 3 years of operation of the LHC in flavor physics, heavy ion physics, and the discovery physics, with the focus on the discovery. And I'll emphasize a few possible connections to string theory, such as study of strongly coupled systems, for instance, heavy ion collisions, the Higgs story and the searches for supersymmetry, including searches for dark matter, and the searches for extraspatial dimensions. The flavor program at the LHC is pursued by dedicated LHCb experiments, but also ATLAS and CMS are significant contributors in selected topics in this area. And among the highlights of the first 3 years was the discovery of this Chi B3p quarkonium state, as well as cascade B star baryon by CMS experiment, measurement of upsilon and psi polarization, first evidence for B sub s to mu mu decay, first observation of direct CP violation in B sub s decays, and strong constraints on new physics from precision measurements of number of rare decay in the bottom and charm sector. This is the result which I just highlighted, the first evidence for the B sub s to mu mu decay, which happens to be very much along the standard model prediction, but it was really the apex of 20-year tour to find this rare decay, which, as you see, has the branching of few parts per billion. On the oscillation front, the LHCb determined most precisely the oscillations, B sub s oscillations in pi ds mode, and you could see the oscillations with your naked eye. It's really impressive how well the detector works and how quickly this data became available. They also observed first CP violation in the B sub s to k pi decays. However, there was no evidence for large CP violation in the other B sub s decays to j psi phi, and even the previous evidence for CP violation in the charm sector has not been confirmed by further studies. On the heavy ion front, we had very successful lead-lead run of 2011. And in 2013, we actually switched to collide protons with lead nuclei. And these runs brought a wealth of new data and allowed ALICE, which is dedicated experiment for heavy ion collisions, ATLAS and CMS, to produce unprecedented results, which really changed the whole landscape of heavy ion physics. From detailed studies of jet quenching in lead-lead collisions to elliptic flow and multi-particle correlations, including the reach I showed you in proton-proton-proton-lead and lead-lead collision, the melting of the excited upsilon states while they interact with quark gluon plasma produced in lead-lead collisions, and a number of other unique measurements. LHCb is now also joining fun with the measurement of the J psi suppression, which is the key element of the quark gluon plasma effects in the very forward region. And one thing which was quite surprising, which happened over the last year, is that we found that several phenomena that were thought to exist only in lead-lead collisions, where the critical temperature is probably reached to produce the quark-gluon plasma, seem to be also seen in lead-proton collisions, particularly when one matches the final state multiplicity of these collisions with that in lead-lead. And this, of course, was not quite expected, and it would be interesting to see how this field changes and progresses given these observations. These are just some of the heavy ion results. The suppression factor for jets in the jet plus gamma collisions, the melting of upsilon 2s and 3s compared to the proton-proton collisions, charm suppression in central collision, and J psi suppression in the forward region in the lead proton collisions. Also, don't forget that LHC has two small experiments, LHCF and Totem, and LHCF measures particle production in a very, very forward rapidity region up to y of 15, and this is important input for the cosmic ray showering Monte Carlo tuning to essentially describe the development of the atmospheric showers induced by ultra-high energy cosmic rays. And Totem measures elastic, inelastic, and total cross-section at 7 and 8 TeV and prove that the Froissart bound seems to be saturated at the LHC energies. So now let's move to the more exciting, the discovery program of the LHC, and let me start with the Higgs story. It, of course, started with the 4th of July fireworks, and the paper which appeared a month later, which showed 5 sigma over 5 sigma in both experiments in several channels. This made a special issue of the Physics Letters B with the beautiful picture of the LHC on the cover and highlights from the two experiments. And now 10 months after, or 11 months after, there are few highlights which actually change the way we think about this newly discovered boson. First of all, we established the existence of new particle beyond any doubts. This is, for instance, plot from Atlas, which shows 10 sigma discovery now, doubled since the July of 2012. In CMS, you see individual channels have significance between 7 and 5 and 2 and 3 sigma for fermionic channel. We also seem to now learn that this is a scalar boson responsible for electric symmetry breaking, as evident, for instance, from its relative couplings to W and Z versus couplings to the photon. Its properties are consistent with those of the standard model Higgs boson within sizable uncertainties, and there is mounting evidence from Tevatron and CMS that it couples to at least the third generation of fermions. The mass of the Higgs boson has been already determined to unprecedented precision in less than 1 year from its discovery. So this is the measurement from Atlas and CMS. And it's interesting that the relative precision on the Higgs boson mass actually exceeds the precision which achieved over almost 20 years in measuring the top quark mass, or for that matter, any other quark masses, which are only known to 0.5% precision. The signal strengths in various channels is compatible with the standard model. Atlas sees slightly enhanced decay rates, and CMS sees slightly suppressed decay rates. If you average, you get very close to 1. And you see this in various channels for both Atlas and CMS data. So within these large error bars, everything looks like a standard model Higgs. Furthermore, both Atlas and CMS strongly prefer the spin parity 0++ over any other alternatives. And in particular, the pseudoscalar and tensor hypotheses have been excluded at more than 3 sigma level in each experiment and for various types of couplings. So what are the implications of the Higgs discovery on the status of the field? Well, the light Higgs boson discovery implies that the standard model cannot be a complete theory up to the Planck scale, and vacuum stability arguments require the new physics to come at a scale of the order of 10 to the 11 GeV or so, which curiously points to the similar scale as suggested by, say, the neutrino mass hierarchy via the seesaw mechanism. Nevertheless, it is possible that a metastable vacuum could survive without new physics all the way to the Planck scale. And while the new boson is light enough to be a Higgs of the minimal supersymmetric standard model, it's yet too heavy to naturally prefer standard model versus supersymmetric solutions. It's also interesting that had the Higgs boson been just 10% heavier than what it is found at, we would have probably stopped talking about low-scale supersymmetry because it would be very hard to achieve. If we found the standard model Higgs boson, we now need to explain the electroweak symmetry breaking mechanism, namely what makes the Higgs potential what it is, what's the origin of the lambda term in the Lagrangian, and it looks more and more like the standard model Higgs boson, as I said, but there's still a lot of room of surprises because the typical measurements are still carried with 10% precision or so. And in a sense, the 125 GeV Higgs boson is maximally challenging and rich experimentally because we can study it in many various decay channels. On the other hand, it probably inflicts maximum pain theoretically, and it's not so easy to accommodate. So, is it a just so Higgs? The simultaneous measurements of the Higgs boson and top quark masses, which you cannot see here, but you could imagine, show us that, well, in fact, it was the first probe which tell us what are the properties of the very vacuum we live in. And we are in a highly fine-tuned situation. The vacuum is really at the verge of being either stable or metastable. And just 1 GeV change in the mass of either the Higgs boson or the top quark would actually tip the scale from the vacuum to be either stable or metastable or unstable. Perhaps nature is trying to tell us something here, so it's very important to improve the precision of the top quark measurements, including various complementary methods. And Tevatron is still leading in the precision of the top quark determination with their new result of last spring. However, the CMAS and Atlas experiments are catching very quickly and soon would overtake the Tevatron. So this is actually this diagram of the metastable vacuum. You see how close we are between stability and metastability, and we now have to decide which vacuum we ended up in. What about new physics? The Higgs is there, but so far there is no sign of new physics, and it's not like we haven't looked hard. This is the plot from Atlas experiment, which shows you all different models probed in new physics, and you see that the limits, typical limits on the mass scale are between 1 and 10 TeV for these different models, and similar plot from CMAS, which breaks it in compositeness, heavy resonance, and so forth. One search, which is quite interesting, which we conducted at the LHC, is the search for extra dimensions and dark matter. In the same way, the dark matter is being sought at the direct detection experiment, where you take the dark matter and scatter it off the nucleus. So now you could turn around this diagram and instead of T-channel, look at the S-channel production of pair of dark matter particles. And this is a brilliant idea, except that if you only produce dark matter, there's nothing you see, so it's very hard for you to trigger in this event. However, what saves us is the initial state radiation from one of the quarks, either gluon or photon radiation. So we could look for the extra jet produced in association with these two dark matter particles. It's a monojet signature, monojet and missing transverse energy due to these escaping particles. And it turns out that in the spin-dependent coupling case, the LHC limits are in fact much better than the limits on the direct detection. In the spin-independent case, where dark matter direct experiment get enormous enhancement from resonance scattering on the nucleus, LHC is not as powerful, but it actually nicely covers the case of the low mass dark matter particle, which has increasing interest since the recent Cogent, CREST, and CDMS result. So here is LHC is also a major player. And of course, you could look into this in terms of limits on the large extra dimensions, and the limits on the Planck scale you get is between 4 and 5 TeV from this channel. We also looked for possibility of producing black holes at the LHC, which would be possible if the scale of quantum gravity is of the order of 1 TeV. And the production cross-section is expected to be very high. It's about the same as production cross-section of the top quark. The signatures, depending on whether you produce semi-classical or quantum-like black hole, could be either large number of very energetic particles, mainly jets, or just a pair of particles if the quantum black hole doesn't have time to thermalize and decays instantaneously. And in all these cases, we actually set the limit on the minimum black hole masses between 5 N6 TeV, essentially ruling out the black holes at the energy of the machine have reached so far. So what about SUSY after the Higgs? 125 GeV boson, as I mentioned, is very challenging to accommodate in over-constrained version of supersymmetry, and particularly for natural values of the superpartner masses less than about 1 TeV. You can see it from these various theoretical studies where you need the masses typical of 3-4 TeV to comfortably live with the 125 GeV Higgs boson. So the big question we need to answer, if supersymmetry exists as the low energy theory, can it still be natural, i.e. offer a non-fine-tuned solution to the hierarchy problem? And now we are actually reaching the question whether we are looking for supersymmetry. We already reached the supersymmetry where we buried this under the ground. Because if you look at the surface, if you look at the MSSM frame, we excluded quarks to 2 TeV and gluinos to over 1.2 TeV. But did we? Well, it turns out that you really need to read the fine print here, because what we excluded is in fact very little. We ventured for an easy SUSY, the SUSY which theorists told us might look like the M-Sucre SUSY, the CMSSM. In fact, it's just a lazy SUSY, which we basically failed to find, but it doesn't tell us much, because nature does not have to be so simple. And what we have studied so far is just a tiny sliver of the available parameter space of low energy supersymmetry, and which was convenient from the point of view of theoretical calculations, but apparently has nothing to do with what nature prefers. So now we're at SUSY crossroads, and since Nima hasn't showed up today, I'll show one slide from his previous talk, which he might show you tomorrow, that this 125 GeV Higgs is really putting us at the crossroad of either the 11th hour naturalness SUSY, which implies light stops and bottoms, reasonably light gluinos and charginos and neutralinos, or we might be at the verge of discovering that supersymmetry, if it exists, is completely unnatural, it's fine-tuned, and then you likely would see long-lived particles, light neutralinos, multi-TeV, additional Z bosons, and so forth. So for the natural supersymmetry, the spectrum is very distinct. You have light partners of Higgs, Higgsinos, then you have left-handed and right-handed stops, and left-handed bottom, which are light, and gluinos, which is fine-tuned to 2-loop level, could be a little bit higher, but somewhere between 1 and 1.5 TeV in mass. The rest of the SUSY spectrum could be very far off, and we might never see it from at the LHC. And that's why these CMSSM-like searches are not very useful, because this is not the bullseye we need to follow. We really need to switch our focus to the left corner of this parameter space. And this is precisely what LHC experiments are now doing. These are the new limits on direct production of pair of bottoms, which set the limit actually up to the kinematic reach of the LHC. The gluino mass up to 1.2 TeV is excluded if the bottom quarks are produced by gluino cascade. You could also look for the gluino-mediated production of stops, and you have a similar picture. This is result from Atlas. You could also look for direct production of pair of neutralinos and charginos, and we set the limits, depending on the model parameters, somewhere between 300 and 700 GeV on the masses of these particles. And you could also look for direct production of bottom and stop, and this is very important and very interesting searches. And you see that we are reaching limits of the order of 600 GeV on the mass of stop and bottom, which really pushes the natural solution in the corner. They're not quite excluded yet, but we are getting there. So the grand summary of our SUSY searches is given on these transparencies from Atlas and CMS. And you see that depending on the model assumptions, actually limits could vary quite significantly. This is the shading on these bars. Sometimes, they vary by 30%, but nevertheless, we are starting excluding the low mass supersymmetry. So what does it take for us to continue this quest and actually either find the natural supersymmetry or show that nature is fine-tuned, which would be a very interesting observation? Well, we now are in the so-called long shutdown 1. There is this screen of the LHC, which tells you that the access is required for about 2 years in order to fix the problems with the machine which prevented us to operate at the full energy of the order of 14 TeV in the first run. And there's a whole bunch of things we need to do, and mainly fix these interconnects between the magnets. And this is a very complicated thing because we now really over-design these superconducting junctions. We now shunt them, we clamp them, we put additional clamping so that there is no chance the superconducting junction could become faulty again. And then we put the spacer between the two bars so that they never touch each other, and we put some thermal shield, and finally color it in a nice gold color. And you have to repeat this about 2,000 times around the whole machine in order to make it working again, and that's why it takes 2 years. So after the long shutdown one, in 2015, we plan to come back at the energy close to the design, probably 6.5 TeV, slowly increasing to 7 TeV per beam. And then we have another long upgrade for the injector, and then we would reach ultimate physics at the luminosity twice the design luminosity of the LHC, which would bring us about 300 to 400 inverse picobarn by the year of 2022. And then the next stage of the LHC is the so-called the high luminosity LHC, which would again double the luminosity and would allow us to reach the ultimate goal of collecting of the order of 3,000 inverse femtobarn, 100 times what we have now, by sometime in 2033-35, by the time the next machine, such as linear collider, could be built. In order to use this potential of the high luminosity LHC, we looked at several different channels, and obviously measurement of the Higgs coupling is one of the most exciting prospects because we could really show that this is a standard model Higgs, or maybe not. And these are the various projections made by ATLAS and CMS experiment. This is in terms of the signal strengths in various channels, bosonic and tau channels. This is where we are now. This is what we expect with 300 inverse femtobarn before the high luminosity LHC. In terms of coupling strengths, you could look at the couplings to fermions versus couplings to bosons. This is essentially where we end up with 300 inverse femtobarn. We can measure couplings to about 5% precision. And if we run for the 3,000 inverse femtobarn, the precision we could reach actually approaches 1% or a few percent on all the couplings. So this is the ultimate precision which we really need to reach in order to probe the BSM theories, which predict that Higgs is not exactly the Higgs of the standard model. The other very important question is that we now have mounting evidence that Higgs is coupled to the third generation fermion, but the only way for us to see if the Higgs couplings are flavor universal or not is to look at the couplings of the Higgs to mu mu. Because coupling to the other second generation things like charm quarks is really very hard experimentally. And this is projections from ATLAS that we need about 3,000 inverse femtobarn at full machine energy to see 6 sigma significance of the Higgs decaying to mu mu. And the other interesting process we could use to probe the couplings to the top quark is TT bar H, where Higgs decays to gamma gamma. Again, you need 3,000 inverse femtobarn to see this process. Interestingly enough, we already start looking for this process. ATLAS is putting the first limit on Higgs to mu mu, which are 10 times the standard model prediction. And CMS sets the first limit on TT bar H to gamma gamma, where we are at 5 times the prediction of the standard model at 125 GeV. So these first ATV studies are already underway, and they pave the way to the new one. Finally, the other strong case for the high luminosity LHC are not just the Higgs boson measurements. On top of this, we also could measure the Higgs self-coupling, which is very important, before the linear collider could do this, and also observe how the vector boson scattering amplitudes unitarize in the presence of the Higgs bosons. This is a direct prediction, of course, of the electroweak symmetry breaking mechanism, and see if there's any other S-channel resonances involved in this unitarization process. We could also rule out the whole class of natural models, not just supersymmetry, but generally natural BSM solutions, and answer the major question: if we enter the desert, or there are still some strongly interacting states below a few TeV, or weakly interacting states below a few TeV, which we can find. And finally, we can probe even higher energy scales via precision measurements. These are just some projections. If we find SUSY in the next run, how well we could measure parameters of supersymmetric models, which might actually tell us something about the baryogenesis, leptogenesis, and maybe even string compactification scale, if it's related to low-scale string theory. And there's several unique measurements which could be done in this domain, which are simply impossible at linear colliders. So, to conclude, the LHC is the most successful and amazing particle accelerator build so far. The first 3 years of spectacular performance of this machine brought us the first major discovery and a whole new program of precision measurement and searches. The LHC is now taking short break till 2015 to come back at 13 TeV energy to explore the terascale with a full potential, and running beyond 2022 with 10 times higher integrated luminosity will be needed for detailed studies of the Higgs sector and any new physics to be found beforehand. The LHC is a very young machine, and it has a 20-plus year long exciting program ahead, which is what we really need to fully explore the properties of the newly discovered boson and see if there is any other new physics to be found. Thank you very much.
Questions? That's great. That really shows very well for our community. Juan.
So you showed the nice plots, you showed that you could exclude supersymmetric particles up to a few TeV. How much higher will it go when you have the 13 TeV run?
So this is shown here. Sorry. Wrong button. So for the, this is LHC 14, which is just 14 TeV machine with 300 inverse picobarn, femtobarn delivered. This is high luminosity LHC, and this is the LHC doubler, the machine I didn't have chance to talk about, but we also discussing possibilities of doubling the machine energy. So you see that, for instance, on squared gluinos in the next run, around 2015, we could reach the limit of the order of 2.5 TeV. The high luminosity LHC pushes us a little bit by another half a TeV to 3 TeV, and then if we build the high energy LHC, it really doubles. And for these bottoms, we are currently a little bit below 1 TeV. We should be able to reach 1 TeV with the full machine energy, and then go to 1.5 or 2 TeV for these two machines. And for electroweak Kinos, we could reach about 1 TeV.
Good. I think we're running late anyway, so maybe we should thank the speaker again.